Okay, today we are going to study related rates. Related rates is about, there are there are several quantities are related, and but each of them depends on another independent variable, such like a time t. So if one of the quantities changes as time passes, then other quantities will be changed too, and the rate of changes of the other quantities depend on the rate of change of the first quantity. Okay. So take a look at a rectangle. For a rectangle, how many quantities you can talk about, right? The width and the length, right? We also know that the area. So we have three quantities here. Maybe the length of the diagonal could be the length of the diagonal, d. Right? The length of the diagonal, d. So those quantities are not independent. They're related. Okay, they're related by the following quantity. The area is going to be the length times the width, and then d is going to be square root of L squared plus W squared. Okay. So now we know that. Suppose we know that the rate of change of the width is 1 centimeter per second. Okay, that's a given information. So at that moment, the width is increasing, but the length is decreasing. It's negative centimeters per second. Okay. What do we want to know? We want to know how fast the area changes. So how fast is the area change? But that change, the rate of change, also depends on the dimension at that moment. So when L equals 10 centimeters and W equals 5 centimeters. Okay. So you think you see the width increase, the length decreases by the same rate. Seems to me there's no change in the area. Right? Second, think about in 1 second, the width increased by 1 centimeter. Right? When we say a rate of change, it means in 1 second. Right? The width increased by 1 centimeter. The length decreased by 1 centimeter. Does the area change? Okay. This is a good problem actually for middle school kids. There's just, we're not talking about rate of change. We just say the width increased by 1 centimeter and the length decreased by 1 centimeter. So originally the size is 10 by 5 centimeters to 10 by 5. So that's the area change, right? Some kids will say without even do the computation, say no change, because the width increased by 1 centimeter, then the length decreased by 1 centimeter. That's, okay. So let's do the computation. How fast is the area change? Okay, the rate of change, right? In area. If it's 0, then there's no change, right? So A depends on L and W. So it's the implicit differentiation here. You differentiate both sides with respect to t, right? And the W and the L are function of a t, so it will be dL dt W plus L dW dt. So that's the formula. Okay. So at the moment, when we don't know the time, okay, when L equals 10, W equals 5, what do we get? At that moment, it is going to be L is going to be derivative of L, so it's going to be -1, right? But W is going to be 5, and L is going to be 10. dW of dt is going to be 1. So actually, it's a 5 square centimeters per second. It's increasing. Okay, based on my computation, it's increasing. Okay, it's increased by 5 square centimeters. Okay, how about how fast is the length of diagonal change? Okay, the length of the diagonal D is going to be square root L squared plus W squared, right? It's going to be L squared plus W squared to the 1/2. So we already learned the chain rule, right? So d dt is going to be, first of all, by the chain rule, and the 1/2 minus 1 is -1/2, and times the derivative of L squared, 2L dL dt, and 2W dW dt. Okay, so you can simplify a little bit, get rid of 2. That's it. And then at the moment when L equals 10, W equals 5, at that moment, the rate of change in the length of the diagonal, it's going to be 10 squared, 5 squared to the -1/2, 10, -1, plus 5, positive 1, because the width increased by 1 at the rate of 1 centimeter per second. Then you simplify it a little bit, right? So numerator is going to be -5. All right? So the denominator is going to be 10 squared plus 5 squared, square root, right? You can take a 5 square out. I think it's going to be -5. If you take a 5 square out, 10 over 5 is 2. 2 square plus 1 is 5. Okay. So you will get, this is a centimeter per second. Okay, what does it tell you? At the moment when length is 10 centimeters long, width is 5 centimeters. If the width increases and the length decreases, we find out, based on my computation, the area increases at the rate of 5 square centimeters per second. But the length of the diagonal is getting shorter. Okay, the length of the diagonal is getting shorter. It's negative. The rate of change is negative. Okay. Yeah, you think about this. This is a double, right? Double the size, and then the width increase, the length decrease. It's hard. Yeah, it's harder to tell, right? The length. I think the length, the width, the length is getting shorter. The width is getting longer. Okay, so this diagonal is going to be, I think, is going to be shorter than the other diagonal. Okay, so it's decreasing the length of the length of diagonal is decreasing. Okay, but the area is increasing. Yeah. So at the moment, here's a 5. Here's 10. Okay, if you increase the width, decrease the length, and you actually increase the area, but it decrease the length of the diagonal. All right, so let's take a look at the triangle, because we're familiar with this type of problem. Okay. the length, the triangle here we are given the information. A equals A is fixed. Okay, A is fixed, and here's a B. Here's the angle theta. Okay, so we are given the following information. Theta is in radians. Okay, so we are given the information d theta dt is going to be 0.2 radian per minute. Okay, so the angle is increasing. And if you do not change the base, you are going to change the area. Okay, so what I want to do here is what I want to do. Okay, we also know that the length, the base, okay, the base is also changing, but I'm going to make it a decrease. This is a centimeters per minute. Okay. So my question is, at the moment, when theta equals pi over 3, how fast is the area changing? I need also when b equals 3 centimeters also. Yeah, the same, because I needed to know the length. Otherwise, you cannot solve the problem. So you have a two undetermined quantities, theta and the b, and the area. So you have a theta, b, and the area. So they're related. Okay, they're related. So when it's pretty similar to the above problems. Okay, you have to find the relationship between theta and b, and the other side that a is fixed. How many of you know the formula for the area in terms of b and theta? Okay. If you have a formula here, the a and a b, that's the angle theta. How do you find the area? How do you express area in terms of a, b, and b and theta? Okay. So if you know the height, right? Half of the b times h, right? You just need to express the height in terms of theta and a. Okay, so that's going to be b, and a sine theta is going to be the height. Okay, so that's so it's going to be half of a, b, and theta. So you have a three quantity. In our case, a is a fixed. So I get b sine theta. Okay, yeah. So here a is going to be fixed. Yeah, a is fixed, right? It's given. Then the derivative a with respect to t is going to be by the product rule. Okay. So that's the general formula. At the moment when theta equals pi over 3 and b is 3. Now, first of all, we are given the derivatives. d theta, this is the 0.1 sine theta, and here's 0.2, right? Cosine theta, this no d theta, yeah. Yes, this is a given. Okay, we have additional information here. This is I think this is a b, right? Yeah, b. The derivative theta, b is negative. This is a positive. Okay. All right. So now, when theta equals pi over 3, b equals 3, at that moment, the rate of change is going to be negative 0.1 sine pi over 3 plus 0.2 cosine pi over 3, and that time b is 3. All right. So let's simply express sine 60 degrees is going to be square root 3 over 2. And 0.2 times 0.3 cosine 60 degrees is 1/2 and times 3. Okay, so you can simplify a little bit. That is going to be the area, the rate of changing area. So rate of change depends on, as a quantities, it's not like it depends on only the rate of change of a b on the theta. It also depends on value at that moment. Remember the problem we did, right? The surface area of the Earth, right? A equals 4 pi r squared, right? So there's two variables here, A and R. A is the surface area, pi r is radius. So if we are given the information, the Earth is expanding at a constant rate, for example, every 1 million years, every 1 million, every 1 million years, the radius increased by 1 centimeter. It's possible. Okay, so let's just assume that increase by 1 centimeter per second. Okay, this is just a ball. Okay, then the rate of change of the area with respect to t naught with respect to r is going to be 4 pi 2r dr dt, and you can see that dr dt is already given its constant rate. So actually, it's a 8 pi r. The rate of change in the area is increasing as the radius increases. Okay, it cannot be uniquely determined. If you just know the radius, the rate of change in radius. Right. So at any time, if you are given information at that moment, the radius of Earth, then you can tell the change in the area. Okay. So you have to say that when r equals 1,000 centimeters, okay, at that moment, the rate of change in area is going to be 8 pi times 1,000, 8,000 pi, and that is a square centimeters per second. Okay. So larger the ball and the rate of change, even the rate of change in the radius is constant. Let's review the geometry. I don't know when did you start the geometry, in high school and middle school, but similarly, triangles is required for this course. Okay, you have two triangles, A and B and C. Another triangle here is A prime and B prime and C prime. So what do we know? Okay, we know this is a B, this is A, this is C. Here's A prime, B prime, and C prime. Two triangles similar by definition. It will be the corresponding angles are equal. Okay. they are similar if the corresponding angles are equal, right? Equal to each other. Right. So for the similar triangles, in this case, you have the following properties. If they're similar, then A over A prime should be equal to B over B prime should be equal to C over C prime. If this is a factor K, and then we also know that the area of the triangle ABC over the area of the triangle A prime, B prime, C prime is going to be K squared. Right? Okay. So that's the geometry we learned before. I hope we still remember that. All right. There is an interesting problem for fun you can look at. I'm not sure you can do it. This is a trapezoid. Trapezoid, okay? And you draw two lines, okay? And you find out that here's 9 square centimeters area. That's 25 square centimeters. Find the area of the trapezoid. Okay. If you can do this problem, that means you are the master of the geometry for that similar triangles. Okay. Okay. So understand, right? Trapezoid cross two lines, and the top triangle, the bottom triangle, you know the area, 9 square centimeters and 25 square centimeters. Okay, so this is a problem test. Any high school kids who claim he's good in geometry. You cannot do it, it's not good in geometry. Okay. It's a good problem, but we don't want to do this problem. We are going to use a simple similarity properties to do the following. Okay. All right. Honestly, majority of high school math teachers cannot do this problem. Not majority, many. If you randomly find meters high school teachers, because geometry is not emphasized in the textbook, so many of them forget this. Okay, but at least we should know this problem. Okay, we have this is a street right. Okay, on the top, we know it's a 15 feet high. It's a street right. Okay. Okay, and someone, it's a 6 feet high. Okay, it's walking away from the street right. So you see the shadow, right? The shadow is here. Okay, so what is given? He is walking away at a constant speed of 5 feet per second. So this is a horizontal speed. Okay, be careful. 5 feet per second. Okay, that's given information. Okay, and what is the question? How fast is the tip of his shadow moving when he is 40 feet away from the base of a pole? Okay, so when in other words, when y equals 40 feet, okay, This is the y. Okay, clear. So think about that. You are walking away from the street, right? And you look at the shadow, right? The tip of the shadow. It's moving too, of course. Otherwise, there's something wrong with that. Okay, it will follow you, right? So I was watching a YouTube video that was a child was so scared because his shadow is following him. He said, "Mommy, this shadow is following me." He looked at the backside. He's trying to run away. The shadow is always following him. He was so scared. So when you walk away from the slide, and the tip of shadow is moving. So how do you measure the speed of the tip of shadow, right? You have to have a fixed point. Let's call it, actually, let's measure this one. This is called x. We want to find out, find the rate of change in x when y equals 40, okay? That's the point. What I know, okay, we are given the following information. We are given the derivative y with respect to t, which is 5 feet per second. That's a constant. So the speed, the person is walking away from the base of the pool for 5 feet per second. Okay, so that means the distance changes at the rate, the distance y, okay, at the rate of 5 feet per second. So clear? Yes. The question is how do you solve it? Okay, you have to use a similarity triangle. Use similarity triangle, this larger triangle, and with the small one take put it here, right? Those two triangles are similar. Why is similar? Because the corresponding angle is the same. This is a right angle, that's a right angle, right? And here's a 6 feet, that's a 15 feet. And this angle is exactly the same angle like this. Therefore, all the angles, the corresponding angles are equal. Okay, so this similarity. Okay, here I have an x total. This is going to be, what is that? That is actually the difference, x minus y, right? Because this part is y, that part is x, so x minus y. So you mark it clearly. Now, according to the formula, ratio, okay, x minus y, the ratio of corresponding side over x, the ratio of the base, should be equal to 6 over 15. Okay, that's the relationship. So now what? You solve for, we have to solve for x, not y. Okay, so x minus y equals x. Let me simplify this first. 2 over 5x, right? All right, so I'm going to get x. So x minus 2 over 5x equals y. So 3 over 5x equals y. So x is always equal to, is proportion to y, is 5 over 3 and the y. When y changes, x changes. X depends on y linearly. Okay, so the derivative of x with respect to y, with respect to t is 5 over 3 and dt. And we already know this is a 5 second. So total is 25 over 3 feet per second. Did I use the distance 40 feet? No. Okay, it doesn't matter. It's independent of the distance, how far you're away from the street, right? Okay, as long as you walk at constant speed away from the street, right, the tip of your shadow moves at a constant speed. That's I did not know that until we finished the computation. this is a this is a power mathematics. You have to compute under some assumptions. Okay. Yeah, this problem clearly tells you 40 feet away, being a 40 feet away, that condition is extra. You don't need it. Now, if you want to find the length of the shadow, the length of shadow, how fast does the length of shadow change, then that is a different problem. Okay, the question, how fast is the length of the shadow change? Okay, I still have to say that when t is 40 feet away from the pole. Okay, and the length of the shadow L is going to be, if you look at the picture again before that, it's going to be x minus y. Okay. And you already know the speed is always constant, right? So dl dt equals dx dt minus dy over dt. And dx over dt is going to be 25 over 3. And the dy over dt we are given, which is he's walking away at a constant speed of 5 feet per sec. So it's a 5. So you will get 10 over 3 feet per second. So the length of the shadow actually increases at constant speed. Yeah. Okay. So if you're running away from the light, and you look at the length of the shadow, and it's increasing at a constant speed. So we're not speeding up, we're not decreasing. Okay. It's increasing at a constant speed, the length. Of course, it's getting longer and longer, the shadow, but it's at a constant speed. Okay. So the next problem is a typical problem. I mentioned last time already. Now this is a 10 feet long ladder. Okay. So we assume that the bottom of the ladder slides away from the wall at a rate of 1 foot per second. So this is we assume that's 1 foot per second. Okay. And of course, the top one also drops, right? Slide down. My question is, how fast is the top of the ladder sliding down? But that is actually the speed is not constant. So we have to say that when the bottom of the ladder is 6 feet away from the wall. Okay. So are you able to set up the equation? I'm going. Let me give you a little bit hint here. This is x. This is y. We want to find out what we are given. Let me write down the given information first, okay? Then you do the rest of them. We are given the following information. Besides the 10 feet long, okay, and we are given dx dt is going to be 1 feet per second, okay, 1 foot per second. We want to find out dy over dt at the moment when x equals 6 feet. Clear? Yes. Can you do this problem? So this is application of calculus. I think the challenging part is geometry. I don't know how much you have learned in geometry. So X and Y are related. Okay. All right. So first of all, you have to find a relationship between X and Y. And everybody knows the Pythagorean theory, right? Everybody, I should say, everybody knows it. Okay. So X squared plus Y squared equals 10 squared. Okay. So X and Y both are function with T because they change. So you differentiate both sides. Okay, with respect to T. So you get 2x dx dt plus 2y dy dt equals 0. So we want to find the dx dy. So dy dt equals negative x of y dx dt. So we are given dx dt, the derivative of x with respect to t, which is 1. Okay, no matter where it is. Now, at the moment, after you find the derivative, then you can plug the numbers. At the moment when x equals what? Equals 6. Okay. Can you figure it out at that moment is a y value? I think it's obvious, right? So this is a 10, that's a 6. The y value at that moment, y must be equal to 8. Okay. It's a special triangle, right? The triangle 6, 8, 10, 3, 4, 5, right? Just double it. Then at that moment, dt is going to be negative x 6, 8. Okay, so second term. That's it. This is how it. So when you get home, before you do the homework, you should look at those problems we discussed in the class. Okay, without looking at the solutions. Can you figure it out by yourself? Then you start with the homework. Formulas we needed to know in geometry, other formulas besides the volume and the surface area of a sphere, right? We also should know the cylinder, the circular cylinder. This is H, this is R, right? So the volume is going to be the surface, the area of the bottom times height. And for the surface area, you have top part and bottom part. It's going to be pi r square plus pi r square, which is, yeah, this one's top, one from bottom. And then the side, okay, this is the top, that's the bottom, this is the side, okay? How do you figure out the side? You have to cut it. You cut this, then you open it, right? You cut one side. That's why, how do you measure the cylinder? You cut from top to the bottom. Then you open it, you get a rectangle, right? The length of the rectangle is going to be 2 pi r, the circumference of the circle. That's why you get 2 pi r times h, okay? That gives the total surface area of the cylinder. Then you have a cone. The cone also has a height and the radius. The cone, of course, is smaller than is contained in the cylinder. So the volume of the cone shouldn't be just pi r squared times h, because that is actually is the volume of the cylinder with radius r. So cone, just cone there, right? So actually, it's just only 1/3 of the volume of the corresponding cylinder. Okay, and here let's put it in the cylinder. If you put it into the cylinder, this is a cone, right? Yeah, this cone occupies only 1/3 of the cylinder. So if you buy an ice cream, one ice cream, the same radius, right? Think about it. One same radius, but the one is cylinder type ice cream, right? Ice bar, for example, right? Another one is just cone-like. And the price of the cone-like one should be just only 1/3 of this. Of course, the material, I don't know the cost of the cover, right? If it's just paper cover. And yeah, you decide if you want to make more money, make a cone-like of ice, ice bar, right? But give them half price, not the 1/3 of price. If you can sell 1,000, then you know how much money you can make, right? Of course, there is a fixed cost, the same cost maybe for the material, the cover. Yeah, so it's easy to do the computation. Mathematics used in some small business. Yeah, honestly, yeah. And you have to, yeah, you have to do some computation to figure it out. Okay. All right. Yeah, later on we are going to also discuss optimization problem. Like if you want to make a cylindrical cylinder, the cylindrical tank, right? And if you know the surface area is fixed, because that's the cost for the material for it, and what kind of dimensions will maximize the volume. Okay, and we're going to start that later. Okay. All right, so now let's look at the problem here. This is a upside down cone, like. Okay, and we know the top one, the radius is going 2 meters wide. Okay, we also know the height, 4-meter height. Okay, and so what is going on here? Maybe we have some water here, right? So let me draw the picture here. It's water. All right. So we assume that water is being pumped into the tank at a rate of 2 cubic meters per minute. So here's the assumption. Okay. Water is being pumped into the tank, okay, at a rate of 2 cubic meters per minute. Okay. So of course the water level is going up. At the very beginning, it's going up very fast, then it's getting slow and slow, right? So we want to find out the rate of basically the rate at which the water level is rising when the water is 3 meters deep. Right. So let's measure the. This is a H, right? So we actually want to find out dx dt, right? It's increasing when x equals 3 meters. So it's very simple. Okay. What we are given? We are given this. We are given the dimension of this cone-like tank upside down. Okay. Okay. We are given the following information. If this is a volume, right? This is a volume. The volume is increasing, right? So V is going to be the volume of the water. So we are given the following information. The dV dt, the volume is increasing because the water is being pumped into the tank, is going to be 2 cubic meters per minute, right? That's all. Besides the radius and the height of the cone. Can you set up the relationship between x and the v? That's all you need. Others are very specific numbers. The radius of the cone on the top, right? It's 2 meters. H, the height is 4 meters. Those are specific numbers. So very first step, you have to find the relation between H and the V, X and the V. Can you do that? So the water is increasing, the volume is constant, right? In order to find the volume, I need to do something here. This is a radius, right? How do I calculate the volume? The volume is going to be 1/3 pi r square x. But how can I express r? R is not fixed. R depends on x, right? When x increases, r increases. I think r proportional. R is proportional to x. Okay. Yeah. So look at the triangle. You cut the cone into half. What do you see is a cross section. It's like that, right? And this is a cross section. And here is a 2. That's just a 4, right? And this is a r. That is x, right? So you get two similar triangles. You got two similar triangles. By similarity triangle, r over 2 is going to be x over 4. That's it. It's not that complicated. So that means the radius is always equal to half of the height. Okay. Then you plug it into here. Then you get the volume. It's going to be 1/3 pi, 1/2 of x squared times x. After simplifying, it's going to be pi over 12 x cubed. So that's the relationship between x and the volume. I know the derivative. I know the rate of change in the volume, okay, which is 2 cubic meters per minute, and that is pi over 12 3x squared dx dt. Okay, so we get pi over 4x squared dx dt. So when x is going to be 3 meters, then you get 2 equals pi over 4 times 3 squared and dx dt. And then you get the rate of change in the height. Okay, so let's do this. This is going to be 8 and 9 pi meter per minute. Okay, so you get this rate. Okay, and actually it depends on the value in general. In general, dx dt is going to be 8 pi x squared. And you see that when the water is getting deeper and deeper, and the rate of the surface level increases slower and slower, okay? Because that's divided by r squared. When r squared is getting larger, then this number is getting small and small. Right. So so we do have to do something to get the similar triangles and use the similar triangles to find the relationship among the sides, okay? Among those quantities you are considering right now. So you must know how to use a similar triangles to figure out the relationship between the quantities in the picture, okay? We stop here.